here is Joshua, and take it away. Thanks again for being here.
Thanks a lot. Glad to be here. So I see some faces some names I recognize. I'm not sure who's new. I'm not sure how many people were at the last talk or have seen it and want to be and don't need to be caught up. So I think it would make sense for me to start by just very quickly giving a brief overview. Does the screen share come through right?
Which is good.
Good. Okay. So still Josh Berne. I still work for Bloomberg. I got contracts into C++26 along with a lot of other people. And this is my overview of the talk I wanted to give. Last time we got through just the abridged version of contracts, sort of just talking about what contracts did at a very high level. I think we touched upon a lot of the things in the second section when discussing details of like the whys of some of it. But I have slides that go into that more. And then there's also lots of other things I can talk about in terms of what we're planning on doing for C++29, which is starting in 2 weeks, really full force in Brno, and then what we hope to do beyond that, once we move forward past the C++29 stuff. Once we have a fully featured product, what do we build on that? So before I begin, does anyone have any open questions or particular things they would like to ask me to cover that I that they don't think I will try to get to in this outline? Just raise your hand. Vishal?
Uh, yes. Right now, I understand. Like, right, we only have um, three tools for contracts.
Mm-hmm.
Maybe a little bit, maybe also kind of levels. But can we kind of have like two different sorts of contracts? One uh, that are exported for user conditions, and one that are internal contracts, stuff that basically describes for people who are updating and maintaining your classes, your libraries, your functions. What are kind of the internal structures that that are not necessarily evaluated when you ship the library to a user. The user library would be like, giving a little bit more broader scope so that the user might can kind of use it properly, but you might have some stuff that while you internally is properly defined, externally for users may not be something that actually uh, you have any sort of guaranteed. So if they kind of do some stuff in their code, you're not guaranteeing that it works, but you know how it's actually supposed to work underneath the hood.
So right now with the MVP with C++26 contracts, you just have pre-post and assert. You don't really get to categorize them or put more information on them. With the paper I'm proposing for C++29 on labels, let me jump forward to show you a little bit about that. Uh, we are proposing a way to basically tack on extra information to each contract. This is an expression that lets you control um, how that contract is controlled, what properties it has when it's evaluated, and lets you group them differently, and then like identify these are the ones that I want, always turned on. These are the ones I want turned on whenever I'm running in production. These are the ones I want turned on when I'm running my unit tests to validate everything everywhere. These are ones I want users to rely on. These are ones I'm going to tell users, hey, these may change at any time with any release, that sort of thing. So all of any kind of extra information about the contracts you want to attach to what are the conditions under which this will be evaluated? When is it true or not? When will we pay the cost to check it or not? Like all those kinds of controls can be encoded in a label, and that lets you express that and then have the same contract different contracts side by side that are categorized differently, and thus, some may be on, some may be off in different builds. Some will be things your users know they can handle one way, other things are not. What we don't plan yet is the ability to actually sort of put on your header different contracts from the ones you put in on your function definition. There's a bunch of subtleties to allowing that to vary that we sort of want to avoid until we have ways to control it. And so to do that, so you still, like, if you really want to have, a different contract for you, like when you use your function through your internal library than when clients use it, like if your internal library knows it can pass values that are like outside the domain of what you want clients to pass, you really just need to give your internal library a different function to call that does that, to make that distinction. Because at the contract level, we don't really distinguish like who is making the call. In terms of what should be true, we just distinguish like when you're building it, what properties will influence whether it's going to actually get checked or not. But the labels just facility, which is in P3400, is really the thing that will let you get that kind of granularity of putting like lots of different contracts with different flavors and different categories in throughout your code that will get like treated differently in different deployments and exposed to different or turned on for different people.
Are also contracts, or are there the potential for contracts to integrate with the compiler system? So if you violate a contract that you basically have a warning or maybe an error that is enforced at compile time. I'm sorry if I'm kind of
So no, that's fine. So during compile time evaluation, contracts will still be checked or not based on how you compiled. So if you're actually like evaluating constant expressions at compile time, then you may get a warning or an error depending on what semantic you've chosen for your compile time contract checking. In terms of like if you just have a function that calls some other function and you're not actually calling it at compile time, but you want to be told, hey, if you call this function in contract, you're going to then call this other function out of contract, and that's a problem. That is sort of what we want all static analysis systems to start doing based on contracts. And like there's been a bunch of work in leveraging contracts for that. And then really, there's been a lot of work historically in leveraging assertions for that. And all of that work can now start using contract assertions for the same things and know that like, hey, user expects this precondition to be true. We should warn them if they have some code path that will call this function with this precondition not true. We do want to be careful that like we do not want a blanket rule that says like it is ill-formed to like to have code that would call a function out of contract or to have a function that couldn't be called in contract, because there's lots of cases where that can sort of arise, especially in generic programming, where you have a function that if you did reach it, it would be bad, but by construction you never reach it, it's not a problem. And identifying that construction and identifying that you've never reached it at compile time is a very tricky thing to do. But like the contracts facility puts enough information there that compilers can start taking advantage of that and start actually warning you and giving you the tools to say, hey, I expect all of these functions to, when they're called in contract, not call anything else out of contract. Tell me if it's not the case and give me warnings and give me static analysis result or feedback that says, hey, these functions are good. They'll never call something out of contract. These are things where you may have a problem you need to go look into. Any other questions right now? I don't see any hands.
Thank
One
you.
quick
Oh,
one.
sure.
Oh,
Hmm.
oh, should I?
Yeah,
I
yeah, go
I
ahead.
know this is not the same thing at all, but I can't shake off the feeling that why does it constantly remind me of the triggers on SQL, on SQL tables, like the pre, the post. Do you like? I don't remember from last time. So when we are having, like, for example, pre-contracts, do we send like the arguments to the function by value, or where we're sending it by like by reference? And would the pre-contract change some argument to the function for whatever reason?
So preconditions and postconditions, when they name function parameters, that they get them as const parameters. So by
Okay.
design, it's very hard to modify function parameters, largely because you never want your program to behave differently in any meaningful way when your contract checks are on or off, because then you can't really safely turn your contract checks on or off. If you turn them off and you were dependent upon them being on, you've now got a Heisenbug where, things worked with contract checking on and they stopped working when I turned it off, or vice versa. And that's always problematic, because then you've lost the ability to, get the performance back when you need it by turning the contract checking off, to find your bugs by turning it on. So constification is our term for like that property where when you name anything outside the contract assertion, the name will be a const L value or R value or const L value referencing that thing, just as a way to prevent you from accidentally modifying these things.
So if I
Um,
send a span, like a function gets a span as an
mhm.
argument,
You get a const span instead.
but usually a span doesn't naturally extend to the underlying span. Int doesn't become a span int const. It
Right.
becomes int a span.
So
Like, sorry, const a span of int, which is different
yes,
from a span int const.
yes. So it is not we to truly get sort of a more thorough prevention of modifications, we would need to introduce some kind of concept of deep const that just does not exist in C++ today.
Okay.
Like we do not distinguish between, const span and span, like use of a const span where you can't modify the span but can modify its elements, versus use of a const span where you're also not allowed to modify its elements. Like the language doesn't capture that.
No, I mean,
And
you can put the const inside. Span
yeah,
const int works, but
mhm,
const span int is not the same thing.
yes, but contracts can't apply that transformation universally to any arbitrary parameter that they might be referencing. There's no concept of, well, I want to not modify things through this variable, so give me a deeply const view of this thing. All we have is the ability to say, give me a const reference to it instead of a non-const one. And that is only on the top layer, but it does prevent a lot of the common modifications you might do.
Thank you.
In general, you do have to know, like, you shouldn't be attempting to modify things with your preconditions and postconditions, because that's always going to be problematic. So we don't actually make it ill-formed. We can't actually prevent it at compile time always, because it may be happening, within some other function you may call that's being compiled without knowing that it's being called from a contract assertion. And we really don't want to sort of bifurcate the language and say, like, here's functions you can call inside contracts and here's functions you can't. So instead we say, like, we have constification, we have lots of guardrails in place to prevent it, but the primary arc of it all is like you should never be modifying things from your preconditions and postconditions, because it leads to the problems we all sort of actively want to avoid and makes contracts less useful. So though, if you work around constification, if you either intentionally or by accident, yes, you can make modifications to the parameters. We don't actively go and copy all of them, and that will lead to bugs. So don't do that. Rob?
I was wondering if, along those lines with constification, if you might have some guidance under conditions where it might be reasonable to sort of violate that yourself. Things that come to mind might be like a precondition which may have to take a lock on some resource to like check for a value that's managed in another thread. or something like that.
Yes.
Are those things that are generally like encouraged, discouraged, or we just don't know yet? Or what's your guidance around this?
I think, and this comes down to sort of what is a side effect and what do we care about, and it's a very hard problem to pin down because it's contextual. Like if you have a lock that shouldn't that should only be taken in a certain order, and you don't know in a particular place if you're going to be taking it in the right order, you should never try to lock it from a precondition or postcondition, because that leads to that leads to deadlocks and fundamental problems that you can't avoid, like that will be introduced by trying to turn on a check that takes that lock. If you have a lock that's only ever acquired and released to read some data structure that you know is never acquired, like there's no further locks acquired, it's safe to do, and it's necessary to safely read that data structure. And the net result of locking and unlocking it is only going to be some, brief pause for any other thread that might be doing that at the same time. Go ahead and do it. That's fine. Like from a user's perspective, if you're thinking about it, you can't tell that lock was taken unless you go and stick in a whole lot of instrumentation to figure out that lock was taken. So it's not going to break your expectations of what's true or not about your program to if it had to take that lock to do something correctly. Same thing for like allocations. Like if you have a program that carefully tracks all allocations and needs to stay within certain bounds, and all your like will start misbehaving if you've used up a little bit more memory than you were planning on it, and your contract assertions need to allocate to do something, that's problematic. But if you just need to allocate some temporary scratch buffer to calculate some result, and then you deallocate it as part of the calculation of whether your contract assertion, and you're not in an environment where that kind of allocation limitation is there, go ahead and do it. So like this question of like what is right or wrong to do in contract assertions is very contextual. And like there's more obvious things also, like putting a printf debugging inside your contract assertions hits on the same thing. Most of the time, like you start outputting a few extra, like, hey, this function was called because your contract assertion is doing that, your program's going to be fine because no one ever looks at your standard output and it doesn't matter. But if you're writing grep and the stuff you put to your standard output is the output that your user's expecting and shouldn't include anything else, then a contract assertion that when turned on starts outputting other trace logging stuff is very bad. Don't do that. So like the answer is like, if you think it will alter the meaningful state of your program, don't do it. If it doesn't, then feel free to do the things that you need to do. And I think this is one of those things where you have to understand what are your expectations for, what stuff is allowed or not allowed within the QOI of your function. Is that?
Yeah, thank you. I was just
sort of
looking for some general guidance on.
Yeah.
Now you've got me thinking a bit more about all the different ways that side effects can kind of come out beyond just modifying the variable directly itself, right? Logging, setting up.
I mean, there's
data
like there's the range of side effects that like the core language considers side effects, which is really like, I mean, reading a volatile variable, things like that. Like all of that is many of those things, like a user calling a function will never consider a side effect. Like you allocated and deallocated some memory because you created a string and used it to do a lookup and then freed it. 90% of application developers are not going to even realize that's a side effect by anyone's concerns because it cleaned itself up and was gone. Printing to standard output, logging a trace message to your logging system. Side effects for not really considered side effects for anyone except the people who are looking at the logging output and looking at the standard output explicitly with certain expectations. But then even things that are just not side effects by as far as the standard is concerned, like, doing an O of n squared search through or a linear search through a data structure that has no side effects, just takes a long time, from the perspective of the user, definitely has a side effect because it made your function take a lot longer than it should have taken. And that can be very real and very tangible, and also is something you shouldn't do. Like don't have contract assertions that, you know, break the complexity guarantees of your function when you call them, even if they have no side effects, because from the perspective of your functions, like the contract you guaranteed to your clients, you have violated your ability to meet that contract by checking that precondition. Like the classic example for that is, you know, is sorted on your binary search function, right? Like I have a binary search function, should take log n time to run, and should only be given a sorted function if it's going to find you the thing you're looking for, or a sorted list if it's going to find you the thing you're looking for. But finding out if it's sorted is linear. You have to walk the whole list. So it's suddenly no longer O of log n time. It's no longer a binary search if you take O of n time to do it. So contracts like that are definitely going to be what we call destructive. They break your contract. They break your contract by just evaluating them. So you want to be very careful to avoid such things. And they're useful to write down. They're useful to have in certain cases. We want to be able to have labels to say, hey, this is in that category of contract assertion, like turn this on and like complexity guarantees go out the window. But, you know, only turn that on sort of in case of emergency, or in the environments where, you know, you're only going to run with very small inputs because you're testing, you know, edge cases that, you know, I passed in, you know, I'm properly sorting all the lists I'm sending to my binary searches. But that can fall over the moment you send in like a million things or do something that's going to really break that down. So yeah, the question of the real heart of it is what is a destructive predicate, and you don't want to write those. The destructive predicates are the ones where, you know, by checking it, I make my program incorrect, or by checking it, I make it correct. If you do either of those things, you have caused a problem, because if you do either of those things, like turn off the check and your program is now correct or incorrect, like try to find out if there's a bug by turning on the check and you break things, or you fix it and the bug just goes away because I turned on checking. That's not helpful. Like that's the problematic case we seek to avoid. And the side effects, like if you completely avoid side effects and breaking complexity guarantees, you're generally fine. And 99% of the contract checks you're going to write are going to fall into that category. And so the guidance is, when you start trying to do the other stuff, be aware of what you're doing, and that, you know, the code you're writing may run or it may not run. And as long as you're aware of that, like you won't start doing the things where you say, well, this may or may not run, but I'm going to do an important thing in it. And then you go, wait, it might not run. I need the important thing done. I shouldn't do the important thing in the contract assertion. I should do it somewhere else. So like this is like one thing that people have thought of, like if you're thinking of this in terms, like if you're correlating this, this question change started with sort of thinking like, is this a bit like SQL triggers? Like it's also, other people look at it and said, like, is this just, you know, a lot like function decorators, where you can sort of run code before and after as a preamble around your function call. And it's really not, because it's also tied to this idea of, you know, it's his code that could run or could not run, and that's very important, because you don't want to use it to just arbitrarily enhance the functionality of a function, because you want people to be able to freely turn these off when they don't need them. So
Thank you. Yeah, that's great.
cool. So I think I will dive into, actually, I keep forgetting I can click on these links and jump straight to this section. So I'm going to talk a bit, since I keep mentioning things in this section and then not actually showing you guys this section, which is when I'm going to dive into sort of the whys of how we got this design. And it really starts with principles. So we were developing the MVP. We started after the C++20 contracts were removed. We started SG21. We started working on, you know, we want a contracts facility. We all have an idea of what we want. And we all keep fighting over, like, contracts must be this, contracts must be this. And a lot of it came down to really like coming to a clear idea of this is why we each feel contracts should behave a certain way. These are the key properties we think contracts should have, because we all had different experiences of, why do we think contracts should behave a certain way? Why do we think we should have a certain features or not have other features? And it came down to one coherent core idea, which we ended up calling the prime directive after much refinement, which was this: the presence or evaluation of a contract assertion in a program should not alter the correctness of that program. So evaluating the program does not, evaluating the property that evaluation of the program does not violate any provisions of its plain language contract. So if you evaluate contract assertions, if you put contract assertions in or take them out, that should never change whether your program is correct or not. It should just tell you, hey, if my program was incorrect and I have happened to evaluate the contract assertions, I find out. If it wasn't incorrect and I evaluate the contract assertions, it should remain not incorrect. It should remain correct. That's the thing that lets us do all the other things we want to do with contract assertions. And this really comes down to wanting our contracts to just identify correctness. And one way to think about this is we think of it as ghost code. Like the contract assertion you write is not really there as part of your program. You shouldn't think of it as part of your program. It's there just to explain to the compiler and explain to your program and explain to your tools and explain to your readers, this must be true at this point. And you shouldn't think of the fact that it can be checked to be true as a part of what the program is actually doing. When it's correct, when things are correct, you shouldn't know it's there. And when you don't run them, you shouldn't know that they're gone. And the moment you have written contracts that have that violate either of those, you're causing problems. And that's all comes down to Heisenbugs. So when a contract is not ghost code, when a contract is actually going to alter the correctness of your program, that gives you Heisenbugs. And that's the problem where, you're running your program without contract checking, some user reports a problem. You want to be able to say, hey, I'm going to do the same things that user did on a build that has all my contracts checked, and hopefully find out something useful that lets me figure out their bug. And then if you can't confidently do that because the contract has removed the bug that they were hitting, you then have to start debugging the unchecked build, which has less tools in it to tell you when things are wrong. And the same thing happens if you now get different bugs that are introduced by your contracts, you have an equally bad problem. So again, a Heisenbug is the ones that appear, that disappear whenever you enable your contracts. And they're hard to debug. They're not helpful when they're there. You want to learn to avoid them. You want to learn to not have them. And we've done everything we can in the language itself to make it so that, they are preventable. Like they're not introduced just by using contracts in and of themselves. Like if you have a Heisenbug, it's because you were doing something weird in the predicate itself that is overlapping with what your function is expecting to do and interacting badly with that. And that's the thing you always strive to avoid. So sometimes it's obvious that you've got a Heisenbug. The classic one is, you go and you increment a variable inside your loop, and you decide, oh, I want to actually verify that this process is always returning true, so I'm going to just wrap it in an assertion that it's true, and then suddenly, not only am I not iterating through, making this an infinite loop when that contract check is turned off, I'm also, not even calling process when that contract check is turning off and my function is not doing anything. Now, this particular case won't compile. This particular case won't compile because I is going to be a const reference to that local that loop variable, and so you can't increment it. But if I just took the ++i out and just put process args I in there, and the constness won't necessarily be correct, protecting me, and the function doesn't necessarily know that process is going to be doing some essential behavior that would be turned off when that's not checked, and that's problematic. So you want to avoid that. But again, you can see this in your function. You can see this by reading the code. That's easy. Like the harder part is when you have more subtle things. Like what if just changing and it's more subtle things that impacted the design of contracts as we were talking about them. Like often when we were first discussing them, we were saying, well, we know the contract violation handler can throw. So if you put a pre or a post on a contract assertion, should that change whether, the the function itself can be no except based on whether you've built the function built with the with a semantic that might call the violation handler or not. Because if you call the violation handler, someone links in a violation handler that throws, maybe that no exception except functions should be able to throw when you violate its preconditions. Vishal,
Yeah.
there's a question.
Yeah, I was just wondering,
Mhm.
let's say that kind of go back to the one where you were saying that yeah, in this one you say like the I is int. Um but let's say that you basically in this for loop you have um like an auto const and um where you're basically passing in the argument I or sorry, the character, what you're actually trying to do. Um, can you do that where the underlying under like have a const reference to or a const reference to your object, um, and you're passing that const reference in your process statement when you're doing the contract asserts or when you're dealing with stuff that's contract. So the underlying process might be changed, but the actual argument or what you're actually referring to is not. So is that one way you can deal with something that you want to basically have that because maybe like you're trying to have something that might be changed through a process outside, but when you're doing the contract asserts, you still want to refer to the same object.
So you can definitely have const references to the same objects. The only difference is when you name the object from within the contract assertion, it's going to have the const added to its type, as opposed to if you named it sort of adjacent to the assertion, and that will somewhat limit the things you can do. But once you're inside the function, once like there's nothing special once you pass that const reference into process to do something, process may then go get some non-const reference or pointer out of that and make some modifications. It's on you to not do those modifications from within a contract assertion. The so like the limitation, the protection provided by constness is really mostly just at the top level to guard against the most obvious cases of, I've gone and modified my my containers or called some non-const member function on a local variable or on a function parameter that's going to clearly state like, hey, this is intended to modify things. That's bad. But you can pass const references to these things around, and your other functions can do things with them. There's no the language within the expression, that the things you can do once inside the predicate isn't limited in any other way. It's a normal C++ evaluation from that perspective. Does that answer that question?
Yeah, thank you. Maybe a little
Sure.
bit of like a example might be a little bit more concrete, but I think that's because contracts are so new. I think
Mhm.
that it's good to ask right now.
Yeah. Um, so again, we have constification that prevents like top level modifications. Um, it's on people to understand, like, don't do things that modify your program state meaningfully deeper inside anything you're going to call from a contract assertion. But the language then had a lot of design points where we had to make decisions. Again, I was talking about, should we have no except go away when a precondition or postcondition might cause a violation handler to throw? Should precondition or postconditions change whether a constructor might be trivial if you put them on a constructor that would normally be trivial? Or should, adding a precondition or postcondition to a lambda make that lambda get bigger because it adds new captures to it? And these kind of subtle changes that would happen just by putting in a contract assertion or just by enabling or disabling the contract assertion are the things we've avoided in sort of all the ways in which contracts interact with other parts of the language. So the answer to all of these questions are no. When you change whether the semantic you build your you build your program with, or you build a particular function with, so that the preconditions and postconditions are checked or not, that doesn't change the result of the no except operator. It doesn't change whether or not that function might throw if it's no except. If the violation handler happens to throw from a precondition or postcondition on a no except function, that's just going to call terminate. If you have a constructor that's trivial, you can't put pre and post on it today. You have to make it non-trivial to put that there, because you don't want pre and post to change like the code path that's used when putting your object into your containers, because that might reveal bugs in your container that go away then when you take the contracts away. Same thing with lambdas. You don't want your lambdas to just grow and suddenly cause allocations to happen when you put them in your stood function just because you've added contracts to them. Because again, then that could lead to, hey, I have a different allocation behavior when I added these contracts and my bugs went away, or I've introduced new bugs. And that's the thing, that we don't want the language silently doing that for you, so that you don't have to learn both how to avoid making when the language will do it and how to avoid doing it when your own predicates, because it's fairly easy to write your own predicates that don't break the correctness of your program. Making the language harder to use by having subtle ways in which it will do it for you is the thing we work to avoid. So there are other high-level ramifications of this prime directive that like we evaluated. Some of these were principles we started with and then sort of refined down to just this fundamental idea of, the contract just shouldn't change the correctness of your program. So one of these is the idea contracts don't see concept, or this is actually backwards. It should be concepts do not see contracts. It is actually fairly surprising if you go through the history of WG21 papers, how many times people typo those two words for one another. And we'll talk about concepts when they mean to be talking about contracts, or talk about contracts when they mean to be talking about concepts. But a concept can't be written that will determine, does this function have a contract or not? Entirely because we do not want people writing libraries or functions that follow different code paths just because you've added contracts to your function. Because then again, you end up with that same Heisenberg problem. So this leads to also, you always want your contract checks, because they can't change the correctness of your program, or any non-destructive contract checks can't change the correctness of your program. They're always redundant. They're always something you could safely run 0 times, 1 times, or 50 times. And the only thing that will change is the amount of like entropy you've added to the universe by evaluating more times. You shouldn't be changing the observable correctness of your program. And this means also that when you turn your contracts off, you don't change like the what your program is doing, so you end up with 0 overhead when you choose not to check your contracts. Vishal?
Yeah. This might be something that I'm kind of curious. Can you
Mhm.
have like contracts that are more probabilistic rather than deterministic? So kind of like, saying that you have a function that might fail 50% of the time, where each individual execution of the problem or problem um, the function is ignored, but as you go over time, as you evaluate the problem, you can have a counter to see how many times it failed versus how many times it succeeded, and is that greater than the significant value of a contract, or is that something that might be needed to be done maybe sometime in the future, not like C++20 29, but maybe C++30 or beyond.
So there's 2 aspects of that. One is like you can definitely have contracts that don't always identify the bug, that only identify a bug half the time because you happen to stumble upon the problem. A good example of that is, again, back to the binary search case. You can check that you've been you can find cases where you are past an unsorted array to binary search by checking if every adjacent pair of things you compare as you're doing your binary search are also in order. You will not be checking if the entire array is in order, but you will find edge cases where, hey, I'm doing a binary search and I happen to check, the 15th and 16th elements and compare them, and the 15th element was bigger than the 16th element. You gave me an out of order array. That's bad. That should be a precondition violation. And so in those cases, you definitely have cases where you check your contracts and you don't know that your program's correct just because they've been checked, but you find some of the cases where your program is wrong because you've hit a violation. The other side of this is if you need to do some kind of analysis that spreads beyond a single point in time, if you need to maintain some state to know, like, is this true? This thing can never be, this thing should never return such and such more than 50% of the time. You need to track how many times it returns something with some condition to do that, and then at the end assert, hey, I was called 700 times, I returned 351 times something that was too big, that's bad. Or I returned 179 times something that was too big, that's okay. You need a place to track that. And right now, we don't have a place to track that. We don't have an idea in contracts today for having data whose sole purpose is to exist for the sake of contract checking, because there's a lot of it involved in that. This idea of ephemeral data that exists for contract checks, we call it ghost data, is really how that idea is evolving. But there's a lot to that, and I'm hoping to see that happen for the C++ 32 timeframe, but we're building towards that in the long term. And I think that once we have the ability to have that kind of ephemeral data, we will be able to really check and provide checks for anything in the language. But it is a fair ways out before we get there. Does that answer that question? Do you have any follow-ups or?
No, I think, yeah, basically, I think the second part of the answer was actually the question or the second part was actually what I was really asking for. Basically, the idea was like for example, let's say that you were trying to simulate rolling a six-sided die. You wanted to know like each of the cases of your die was your die was fair. So basically, like you could probably do something with contracts to keep track of how many times you rolled the die and see if it's close enough to your expected output. And that's what you're just saying that right now it's not built into the or into the contract specification, but that's something that might be coming sometime in the future as contracts developed.
Yep.
Thank you
Yep.
again.
One of the key sort of design points that is subtle to spot, but is very much there is, contracts in C++ 26 and probably contracts in C++ 29 are sort of point in time checks. They don't really support spreading out like the logic of the checking across many different points in your program. So if you have to be able to look at your program state and say, hey, is the thing I'm checking true or not based just on the state right now? And if you can do that, you can write a contract check that does that. If you can't do that, if you need to sort of say, hey, I need to gather some information here, maintain it this way whenever the user does this, and then I can see if there's a problem later based on the stuff I've gathered, that's a sort of a much bigger problem that you can achieve today by just saying, hey, I'm just going to have my program gather that information unrelated to contracts and then use the information I've gathered in my contract checks. But you can't do the other way where you say, hey, I'm only going to gather the information when I actually want to check the contracts. And I want to tie those two things together. That's a thing that we hope to bring later. So again, the other last side effect of the last aspect of the prime directive is that any other behavior changes, any other behavior doesn't change whenever you change your evaluation semantics. If you ignore your contracts other parts of the language aren't going to start behaving differently. If you enforce them, other parts of the language aren't going to start behaving differently. And again, this comes down to, any destructive checks, we want users to be able to look at their functions and go, hey, I'm going and modifying a bunch of other variables when this check is called. I can see the code that does the modification. I know that's bad. I shouldn't do that. And then, but you don't have to go and say, hey, I put this in, and then suddenly like my vectors started going down different code paths and allocating differently, and that caused other problems. We don't let that happen. So again, I talked a bit about sort of our idea of what a destructive predicate is. That's the thing you want to avoid. And everything we've done has been making sure that we prevent destructive predicates as much as possible and encourage you to not write destructive predicates. And the language doesn't make your predicates destructive or your contracts destructive just by putting them in there. So there's a bunch of things I've already touched on sort of why or what we've done to make that happen. One of the things also, like I said, contract assertions may be evaluated on function contract assertions pre and post could happen, and regular contract assertion statements can be evaluated 0 or many times depending on how you built your program. This is another thing that also helps to make sure you don't write your destructive predicates, because if you go run your build and say, hey, I want to both compile these translation units to check all my preconditions and all the preconditions and postconditions of functions they're calling, and I'm also linking to a library that's built to check all preconditions and postconditions when called into that, I'm going to be checking all those pre and post conditions 2 times. If any of those preconditions and postconditions are destructive, they may hit on the second check when they didn't hit on the first, because the precondition or postcondition made it so that it was violated itself the second time it was checked. And that's bad. And that, again, because you can evaluate them multiple times, that helps you actually ferret out destructive checks that you didn't want in your tests. I've actually found destructive checks this way by putting this into our assertion library, where I basically said, hey, I'm going to change my assertion so they just, run in a loop a certain number of times if a certain macro is set, check every assertion 10 times. And then I found places where, someone was incrementing something inside the predicate of assertion, and they got very bad results because they started incrementing it 10 times instead of once. And that was immediately spotted, this is a bug, I need to fix it, and take the increment out of the assertion because it shouldn't have been there in the first place. But again, like I've also said, avoiding non-destructive predicates is actually fairly easy. The simplest is just don't put side effects into your function. Like don't do things that have side effects, and you won't have problems, including complexity guarantee related side effects. But when you do have them, don't do things that your function is depending upon. Don't ever think, okay, I'm writing this predicate, and the predicate will do the part of my function that needs to be done. The moment you've done that, you are going to have problems when that predicate isn't evaluated. So don't allocate and then depend on that allocation being there. Don't do things like I'm going to lock my data structure in my precondition and unlock it in my postcondition. That will never work. You can do tracing and telemetry. You can lock and unlock your shared data structures as an atomic thing, doing your check. You can allocate and then deallocate. That's all fine. Again, it's all also contextual. It's if you're in a particular environment where those things are going to be problematic because you're very sensitive to how many locks you're doing, how many allocations and deallocations you're doing, you're going to have contracts that cause problems with that because you are depending upon those allocations and locks not happening when you call your function. But again, these things are all fine to do in the majority of cases for the majority of application developers. And then again, like I said, the idea you had of doing sort of tracking of number of things, having ghost data associated with your ghost code ephemeral data that lets you sort of maintain state and use that state for your checking. It's just not a feature we have yet. It's coming later. So you can't do things like count the number of invocations of your function, can't track state between multiple assertions. That's in the future. We also had other principles that guided like the actual contracts feature, like what do we mean when we say minimal viable product? How do we get here? When we say minimal, a lot of people look at it and go, but there's so much stuff in here. You can talk about it for hours and hours. How could it be minimal? Really, when we say minimal, we were throwing out anything that was contentious and anything where we weren't sure of the answer, we took out of the feature. But we didn't take things out simply for the sake of making things smaller, because we were also seeking to make something viable, something that was going to be useful and a product and something that will serve the needs of many C++26 users and then build towards serving the needs of most C++29 users. So that's where viable and product came in. That's the things we were working towards and designing as we went. So again, these led to principles during the design. These led to things that guided the feature. So with each of our decisions, we never made decisions that blocked things we knew people might want to do in the future. Anytime we had cases where we couldn't come to an agreement on what something should do, how something should work, we said, let's make it ill-formed to use this, to use contracts in this way. Like there was a lot of decisions on like, should contracts be allowed on virtual functions? How should they behave? In the end, we just said, you can't put contract assertion pre and post on virtual functions in C++26, because that leaves us maximal freedom to put them on virtual functions later and have them behave however we want later. So I can then go into like pre and post and contract assert are three kinds of contract assertions. I think with those principles, this is what we captured. This is what we provided. So this kind is the pre-post and contract assert are the syntax that lets us write contract assertions. They also specify exactly when is that contract assertion evaluated. Pre and post and contract assert each have different rules for when they are evaluated. So pre is whenever your function is invoked, it's going to get called. It's exactly after function parameters initialized, and it's exactly before anything in the function body gets evaluated. On constructors, this means before your member initializers, before your base initializers, before a function try block is entered, the preconditions are checked. It's got some limitations. You can't put them on virtual functions. We plan on fixing that. It can't put on defaulted special member functions because that might change whether the special member function is trivial. We might go fix that. We might go fix that later if we can come to consensus on that. But other than that, you can put pre on any normal function. It will always be checked after your function parameters are called. It can use them. And then you will enter your function body after it's checked. Post is called after the function values return, after the return values initialized, after local variables are destroyed. Again, this is just like pre, this is on the boundary between the caller and the callee. Pre and post can both be checked in the caller's translation unit by the code that's laid down to call the function. They can be checked in the callee's translation unit after the function transition has occurred into the library you're calling into. Whenever you're in a post condition and you name a by value parameter, it has to be const. This is separate from constification. It has to be explicitly const. This is because if it's not const, you are talking about a by value parameter that only the caller can see. It makes no sense to tell the callee, or it makes no sense to tell the caller anything about that function parameter if it's not const, because the caller doesn't know what the function is actually going to do with that variable and can't get reference to it or understand its meaning. And if it's not const and the modifications can happen to that variable, then your post conditions essentially end up meaning nothing. You can name the return value, again, just like any other function parameter, any other variable outside the predicate, the return value's name will be a const reference to the return value when you make use of it. Just like pre, you can't put them on virtual functions, you can't put them on special member functions. You can't name parameters in coroutines because those parameters, by the time post is checked, will have been moved out of and copied into coroutine local variables. This is actually a side effect of the fact that they must be const. If you try to make coroutine parameters const, and then the coroutine itself, the coroutine body itself won't compile because they must not be const as far as the coroutine is concerned. And there are cases where, surprising things can happen when you have function parameters that are things that can be put in registers to pass through, because your post may see different variables in the caller and the callee if those things have been modified. So if you have an int parameter and you check your post condition on the caller side, the int is going to be put into a register and passed to the callee. And then the callee is going to use the value in that register. And if the callee casts away the const and does something with it, it will be able to modify its local copy of that int parameter, and the caller will never see that modification because there's nothing in the ABI that says, hey, I passed you a value in a register, you better pass me its final state back. And we don't want contracts to change the ABI to pass that information back. But again, this all depends on having done weird things in the first place to modify const parameters, which you shouldn't be doing. And then contract assertion is our final contract assertion. It's a statement. We added a new keyword for this because it can't be a contextually an identifier with special meaning, because it can occur anywhere in any expression or in any statement. You can put it anywhere a statement can go. It's useful for any kind of heuristic checking you want to do of preconditions and postconditions that happen within your function body. It's useful for wrapping calls to other libraries and checking that they're behaving properly. So contract assert the preconditions of a library you're calling before calling it. Contract assert its postconditions after it returns, even before that library has added its own assertions. Checking loop invariants, checking things in coroutines about like, what is my state whenever I get resumed? What is my state before I suspend? We cannot use contract assert as an expression, because to do that, we have to come to an agreement on what no except contract assert means, and different people have different opinions on what this means. I think it should always be false, because that contract assert statement will never throw an exception in correct code. Other people get concerned by that because a throwing violation handler might actually cause that to throw. But again, it comes down to sort of coming to agreement on that, and how much we let the principles guide the other aspects of the language, like how the no except operator behaves, before we can make contract assert into an expression. Assert in C, the assert macro is an expression, can be used. There are a lot of people who like making use of it inside their expressions. It'd be nice if contract assert was able to use an expression, and we hope to get there someday, but it's sort of on the back burner until we can decide other things. Like I said, we call pre and post function contract assertions. Those are the things you actually can put on the declaration. Someone asked about this last time. This is where I actually got to state it. The first declaration of a function is the one that must have them. You can then repeat them on other declarations, and they must be the same, or you can skip them on other declarations. You don't have to have them there. So in general, you put pre and post on your declaration in your header, and then you don't have to go repeat them anywhere. And it's only when people go redeclare your functions themselves, or where you have things where you put your function declarations in multiple headers, that you need to make sure you duplicate them properly. If different people see different contract assertions for the same function, you end up in a state where your program is ill-formed, no diagnostic required. Don't do that. The only thing that can change between different declarations with pre and post is parameter names. Template parameter names can also change, but other than that, they have to be identical. And because they have to be identical, and because lambdas are weird and compilers treat lambdas weirdly when they're in different places in the source code, even if they're otherwise identical, you pretty much can't redeclare a precondition or postcondition that has a nested lambda within it, because that nested lambda will always have a different type, and this will not be the same. So in those cases, you have to just put the precondition or postcondition only once on the first declaration and not somewhere else. So predicates are the expressions that we put in pre and post. It includes the conversion to bool. So anything we say about like if the predicate throws an exception, if the predicate returns true, if the predicate returns false, it includes the conversion, and if that conversion is a user-defined conversion operator, and that throws, it's part of the predicate when that happens. Anytime we have a checked evaluation semantic, so observe, quick enforce, and enforce, that determines the result of the predicate. If it's true, you don't have a violation, you go on. If it's false, there's a violation, you call the violation handler. If it throws an exception, we treat that as a violation. The violation handler is going to get called. If it can be predicted, which means a compiler can look at your predicate and go, hey, I know this will always return true, or I know this will always return false. I did. Then the compiler can skip your contract assertion entirely, and that may mean all your side effects of your contract assertion get skipped. But in practice, I don't there are a few predicates where this particular condition is going to apply in a way you can observe. They're their own scope. Inside that scope, you can name function parameters; those get constified. And also, whenever you have a contract assertion, again, because we don't want contract assertions being present to change the size of lambdas, contract assertions can't add captures by naming variables inside a lambda that is doing explicit capturing. They can use captures. If you name something that would be captured, it will refer to the capture and then not compile if nothing else captures that same thing, if it's neither explicitly captured or captured within the body of the lambda. And then the last two bits are evaluation semantics and the violation handler. I've named a lot of these already. There's 4 different things contract assertions can do today. They can be ignored, observed, enforced, or quick enforced. The primary distinction here is, does the predicate's result actually get determined? And then what happens when you have a violation detected? Quick enforce skips the violation handler. It's the thing that has the lowest overhead in terms of code size, code generation size. The purpose of it really is when you want simple checks, when you don't want to support a custom violation handler, you want to just use as few bytes as possible and still have checking. You want to select quick enforce. This was driven by the libc++ guys doing a lot of analysis of what does it take to turn on their assertions everywhere. And they found that there was significant overhead of having function calls around each assertion, of having the full information related to populating the contract violation object of we want to track the line where the violation is happening, the expression that was checked. They want to strip all of that out and just say, hey, you call vector operator bracket without a bounds, your program should just shut down immediately and tell you as little as possible. You can get that information out of your core dump by looking at where your program actually hit the termination, what the stack was. Enforce and quick enforce, or enforce and observe, give you more information. They populate a contract violation object. They call your violation handler. They let you propagate the information about what happened through whatever logging system you want in whatever useful way you want. So you don't have to rely on other tools to get that information after the fact. The evaluation semantic can be different every time your contract assertion gets called. It can be different in different parts of your program. You can link all of these things together. It's all based on how you build what you have asked your program to do when you built it. Did you build this TU saying, hey, check all my contract assertions, or check everything that I'm calling, or check everything that calls into me? And mostly right now, the decision is, per TU, call the side. So when I build a TU, I'm going to build the functions in that translation unit. Every function in the translation unit will either check all its pre and post conditions or not. It will either enforce them, observe them, quick enforce them. But as time goes by, we expect to see, and we already have some options to say, hey, check all these things caller side, check all these things, check only preconditions, check only post conditions, things like that. and more fine-grained control we hope to see in compilers in the future. So like I said, pre and post happen exactly on the function called boundary. They can be configured per TU. They might be evaluated in both cases. That could happen with different semantics. It's all a side effect of how did you build your program? What are the needs of the person building the client libraries? What are the person building your libraries? And what does the application engineer who puts it all together ask for? With our check semantics, observe, quick enforce, and enforce, you always end up getting a diagnostic or getting your violation handler called when there is a violation. One of either in quick enforce, your program's terminated, and enforce and observe, your violation handler is called. And enforce, your program will get terminated if the violation handler returns normally. And there's almost always some code generated and some runtime cost to when you have these. We call quick enforce and enforce the terminating semantic because they share this property that control never continues into the code that follows immediately after the assertion if you have a violation. And this lets some people feel more comfortable reasoning about what the function does when thinking about, like, I put this contract assertion in here, and now I know for sure, I'm never going to get into the body of this function in this bad state. Generally, you want to know this based on how you built your program. I built with enforce, so I don't need to think about, like, what is this function going to do if these preconditions or postconditions were violated, because I know that they've been enforced and I couldn't have gotten into this function in that case. This also lets some optimizations happen because the compiler knows that enforce or quick enforce are happening. It knows that these conditions will be true. It knows it can elide branches and do all sorts of other optimizations based on the predicate being true. It's possible implementations might introduce their own semantics. The system sort of allows for that. We are fairly confident that we will see the assume semantic, which is basically saying, hey, make it undefined behavior if my contracts are violated. Whether we standardize that is a question for the future. And we may see other semantics that allow you to do things like say, hey, I want to, again, treating the question of, make this contract assertion, make it a violation if this contract assertion is violatable by this code, can be thought of as a compile time semantic for a particular contract assertion. So we might see compilers start to roll out things like that. There were proposals in the last meeting for something called compile assert or constant assert. That sort of boils down to just another contract assertion semantic from a lot of perspectives, and we might see it come back as a proposal like that. During constant evaluation, I've touched on this a bit. You also get to choose, your contract assertions will also be evaluated with some semantic or other. It might be observe, it might be enforce, it might be quick enforce. What you do not have at compile time during constant evaluation is a link time contract violation handler. Because the contract violation handler is a global thing you do at link time. When you're doing constant evaluation, you're doing that as part of compiling a particular translation unit. So instead, when you quick enforce or enforce, your program is just going to issue a diagnostic and in BL form. When you observe, you're going to issue a diagnostic and keep compiling, and you get a warning. And when you ignore, you will just ignore the contract assertion and not know whether it's been violated or not. But importantly, when you choose whether to enforce or not, when you evaluate these things, it can't change whether a given expression is a constant expression, because again, that would fall into the same trap of being able to spin on whether your contracts are violated or not, changing code paths based on contracts being violated. We want to avoid that. So if you have a contract assertion that is evaluated during constant evaluation and it's calling some runtime function, it's just going to be a hard error. Your program will be ill-formed. It won't fall back to runtime because your contract assertion is doing that. And the same thing will happen in the other direction. You can't something can't be treated as a constant expression because of the predicate and then, fail because it happens to require evaluating at runtime. So this is why if you know the way like constants behave when they're initialized and how those can sometimes be treated as const expr things and sometimes be treated as runtime variables, happens because of a process called trial evaluation, where you sort of, the compiler will evaluate the expression and say, hey, could this have been in a constant expression? If so, it is. And the way we implement that with contract assertions is when the trial evaluation happens, it happens with contract assertions all ignored. It skips them completely. And then that determines is the expression a constant expression or not. And then whether or not they're checked when the actual expression's real value is determined is based on however you're choosing to build your program. And at that point, you get a hard failure if you hit a contract violation. And then the last bit is the contract violation handler itself. It's a replaceable function. You selected at link time. You can only link in one. Here's its signature. It lets you do all sorts of different stuff, primarily in terms of how do you want to report your violation when it's happening. I mean, I think the thing we will see evolve for the most part is the same people who write your logging systems are going to provide a contract violation handler that ties into that logging and reporting system the same way all your other logging functions do, because you want to log a contract violation and get all the information formatted nicely and delivered in a way that you can then, be aware that it's happening and act on it in some useful way. You can also use the contract violation handler as a way to cause contract assertion failures to turn into an exception. This is a thing that can let you do some amount of recovery in certain situations. It doesn't magically get around things like having no except functions. If you choose to use exceptions in this way, there are lots of ramifications on like other ways in which you write your programs that you need to be careful of, in particular around how you use no except and how much exception safety sort of all of your functions need to have. But it is a facility that's there if unconditional termination is not an option for you. The contract violation object is an object we've built so it can be extended. These are the current properties it has. We put a lot of work into it. You can think of it a lot like sort of the type info object. It's a thing that the compiler creates, the compiler owns it. You're not allowed to create your own instances of it. You're given a reference to one. Its lifetime is only guaranteed to live through the life of the contract violation handler. And all of this is to make it so that, the code you write in your violation handler, the code you write in your different translation units that uses contracts, none of it is tied to each other through particular ABIs for the contract violation object itself, so that you can, build your contract violation handler with one version of GCC and libc++, build your translation units and your functions with libstd++ and a version of Clang and link it all together, and it should all end up working together seamlessly. You can also, none of the things in the contract violation handler are guaranteed to be there by the standard. So it is conforming to say, have a build where you say, I don't want any, information to leak into my binary about, what my code looks like, because I'm putting my binaries on machines I don't trust. So strip that all out, and the contract violation handler is going to get called. It's not going to get told line numbers and source locations. That will all be blank. So that's all conforming, and if you choose to build that way, that's what you get. But we do want to capture all the information that might be readily available, so that's all in the contract violation handler, in the contract violation object. And that's sort of my deep dive into sort of everything we have done so far. Those are all the major parts. That's how it behaves. That's what it looks like. That's sort of a bit of why we did things the way we did. And I think now I'm going to open up for more questions before going into like what we're hoping to do next. If anyone has any more questions right now. I've gone a long time also. So, Vincent.
Yes, Josh. First of all, thanks for the summary. It was really great. The question that I have is, you presented a lot of items that effectively becomes the onus of the user, right? Creating a contract that doesn't have all these side effects. You listed a laundry list of items. Can there be a tool or even leverage the compiler in some way to present this to the user that they are creating a destructive contract by having side effects? Because it's typically depending on the full scope, and the compiler kind of has that. So I'm just thinking, is that something the standard should add? Is that the compiler should add? What are your thoughts on that?
I expect to see some compiler warnings on this kind of thing. It is a challenging problem to get right because of how contextual it is. Like, you do not want to make it ill-formed to just put a printf into a function because some like higher level library happens to be using that function inside a contract assertion. So a general, like, this is invalid to do would be bad and would be highly problematic. And then I think that just generally identifying are there side effects you do care about and filtering out the ones you don't is not simple, but there's been a lot of work in that direction. Like, Clang has warnings exactly on this subject of like, warn if assertions have side effects. I forget how they actually spell it, but I expect to see that same kind of warning tied in for contract assertions. But I think it will stay at the compiler level as a warning, because getting it exactly right, specifying it in a way that doesn't preclude important use cases or make contracts sort of not deployable in many cases, is not something we want to bake into the standard itself. But I think compilers will do all sorts of stuff to help you find the obvious cases where you've done something silly, where we can't prevent it in the language itself. And I think at the end of the day, because like, one thing I didn't touch upon was like the C++20 approach to a lot of these questions was, oh, just make it undefined behavior. If you have a contract with side effects in it, it's undefined behavior. Like, anything can happen. We're not going to make any promises. Nothing in the C++26 contracts took that solution as an option. We have very clear explanations of like, if you have a predicate that does certain things, it's going to evaluate an unspecified number of times. You'll be able to figure, based on your build configuration, how many times it might evaluate, but it will evaluate, and it will follow the rules of C++ evaluation when doing so. So you can reason about, what happened. Like, oh, I put, a plus into my, or I'm incrementing some variable inside my contract assertion. It's going to get incremented. It's not just going to go and, jump off and eat dragons while running because it's UB. So you can reason about these things. Your compilers can produce warnings about these things, and I expect to see some existing compiler warnings about assertions sort of repurposed for this in contracts. But getting it flawless to the point where we could reliably put these things into the standard, I don't think that that's going to happen, because it is contextual what is and isn't good, and we don't want to prevent realistic use cases by putting rules into the standard that make it so you can't easily use contracts where you need to.
Okay, no, that's fair. I could imagine that it won't be baked in the standard to be a compiler feature. I do have a follow-up question, if that's okay. So the question I have is related to the handler. You mentioned that there's only one contract violation handler within the whole scope of the program. What was the reason for just having one? And would there be benefits of having, because I personally see benefits of having more, but maybe your insight is much more depth than mine.
So part of it is because having one contract violation handler was one of the reasons Bloomberg first went to the C++ committee to try to propose contracts in the first place, because we have gotten a huge amount of benefit from having one contract violation handler for all of our assertions throughout our whole company, because it lets us, treat uniformly all the bugs that we have, know where they are, except our reach for that extends through, the millions and millions of lines of code we own and write. It doesn't touch any of the third-party libraries we use. We want to be able to do the same thing with all the third-party libraries we use by saying, hey, you hit a contract violation inside, your standard library, inside some Kafka thing you're running, inside whatever. We want that to flow into the same logging mechanisms and tracking systems and everything else that all of our other contract violations handlers can do, so that at the end of the day, our managers can look at each group and go, these guys are running programs hitting contract violations this often. they need to be given more time and effort to fix bugs, not asked to do more things wrong. And these guys aren't, and they can keep doing more stuff, and they're doing great. Yay, give them a party. So having a central violation handler is one of our big motivations for, why we want this, because we want all our third-party libraries to report bugs in the same way as all our own libraries do. Having library-specific handling of bugs is a thing that can be useful, but in practice is not something we've seen as a strong motivation for wanting contracts in general, because if you want library-specific handling of bugs today, you can do your own assertions just in your library that do that. And most of the people who want to do that I've seen tend to want to do it so that their library can, fix their bug when the violation happens. And that's exactly what contracts are not the right tool for. I think this doesn't mean that we don't intend to have this as a functionality later. The labels proposal also includes a way to say when a particular label's on a contract, it should first call this local violation handler that might, skip the regular violation handler entirely. And a label is a way to do that, to say like, hey, on this set of contracts, we want some specific local violation handling when those go wrong, because it needs to be reported to particular people, or because it's in a particular sensitive area where certain things should happen when there's a violation, or certain cleanup must happen in all cases, stuff like that. So that is a part of P3400 that we're hoping to land in C++26, but it's not part of C++ in C++29, not part of C++26, because again, the primary motivation of wanting to have it in the language is to get that global violation handler, because that's important for like running a big business that we do. Right? That's why we are here in the first place. Like that's the thing that gets my management to keep funding me coming to WG21, is to be able to say, hey, at the end of the day, Bloomberg is using all these different libraries, all these different things. We want them all to behave consistently so we can manage our problems and know where they are and fix them, and not have to spend all our time engineering like, well, this library reports things this way, and this library reports things this way, and this one does it this way. We write one violation handler and it handles all the bugs that are found by contract violations in all of our libraries.
Okay, no, I appreciate that. Thank you.
Sure. Jim was asking something, but he lowered his hand.
Well, I lowered my hand, but I was going to put it in the Discord. But you had mentioned just a minute ago trial evaluations, and so not being familiar with that, I quietly go off and Google it and check on CPP reference, and I don't find anything. So if you have anything on that, or if you could give us a crash course, but this might be off topic, so your discretion. If anybody has a link, if they could throw it on the Discord.
I don't know if there's a good link for it. It is esoterica related to what happens when you use integer or integer enumeration const variables whose initializer is visible, because const expr variables sort of evolved from those. Like in C++03, we didn't have const expr variables. We just had constants. But you could use a constant as like a array bounds if that int had an initializer that was viewable and evaluatable at compile time. And so what happened is, like, as const expr was put into the language, it interacts with these non-const expr variables in a way that where they sort of look const expr if they can be and don't if they can't. And there's a lot of complexity that in terms of, or subtlety in terms of how that interaction happened. And I think we actually just took the word trial evaluation out of the language itself and called it something else. And I'm blanking on what the name was, and that was only, it was only like a few weeks ago that we did that. But fundamentally, it's this idea that a constant with an initializer that could be const expr behaves just like a const expr int. A const expr with an initializer that's either not visible or that isn't const expr because it, references something that's only available at runtime, just behaves like any other int. It just happens to have a type that's const, and it can't then be used in constant expressions and other stuff. And the way that determination happens is through this thing called that we used to call trial evaluation. And I can check later if there's any good.
Yeah, if anybody has a link or a crash course or something, because that is kind of as you're describing it, more a boundary where it hurts my brain between the const expression and other const things. And fundamentally you get it, but there's a lot more subtlety clearly, if these terms like trial evaluation are out there, which kind of, yeah, you kind of suspect it is. But anyway, so I'll take it offline, but thank you.
Yeah, I mean, we wrote some papers explicitly when digging into this exact topic for how should contract assertions behave during constant evaluation, because getting this right was a non-trivial part of the design, and I think those had some good explanations of trial evaluation and how contract assertion evaluations interact with that. I can find the papers. I think I had one section of one paper. Timur wrote a paper sort of trying to go into more detail on just that subject, and I can dig that up. So put something in the Discord and I will reply. So any other questions?